Hey, welcome to the Bat Cave. Bats are an amazing evolutionary success stories where more than 20% of all mammalian species have been created in a really short, intense period of adaptive radiation. And we believe today that a critical enabling factor for this success story has probably been this unique combination of biosonar sensing and flapping flight, because bats have these two abilities. There's nothing in current sonar technology that could keep up with bat biosonar, and there's nothing in current drone technology that could keep up with bat flight. Besides looking at bat biosonar and flight in isolation, there's actually the combination that poses an even greater intellectual challenge. And that is what this lab is about. In engineering, controlling a machine with lots of degrees of freedom usually requires likewise highly dimensional sensory input. In bats, that is not the case. Bats have about 20 discrete degrees of freedom per wing, and they control all those degrees of freedom just based on two one-dimensional sensory inputs, the two echo trains that they receive at their two ears. And these echo trains convey all the sensory information about the environment of the bat that the bats need to do their aerial acrobatics. So how does that work? So in our bat lab here, right in the Sunderland Global Biodiversity Hotspot, in the heart of Southeast Asia, we are looking at different bat species that have particularly sophisticated biosonar systems and also flight maneuverability. And we want to understand how these animals link biosonar sensing and their flapping flight. For this purpose, we have constructed a setup that consists of synchronized arrays of high-speed video cameras and ultrasonic microphones to collect the big data sets that cover both flight and biosonar functions. We have also been working on deep learning approaches to make sense of this data, and you will now learn more about our experimental approach and our data analytics as we take you through the lab.
So welcome to the tunnel. So for the combination of the optical and the acoustic side of the bat, we want to be able to blend the biosonar and the maneuvering flight. So we have ultrasonic microphones and an array of high-speed cameras to capture all of that data. The acoustic side of it will have like acoustic wave reconstruction with their algorithm to reconstruct the sound of the bat anywhere in the tunnel. And on the optical side, we have the optical reconstructions to be able to reconstruct the maneuvers or what the bat looks like at anywhere in the tunnel. My mission here is to see how can we do more maneuvering flights, because we can reconstruct straight flights. And for the purpose of reconstructing all of these like different maneuvers, we have these obstacles here in like a stochastic manner, such that when the bat comes in, it wants to dive or turn in order to avoid the fishing line, which you can see with its echoes. And it's been really successful this summer with getting a bevy of different kind of maneuvers. We have like diving, we have looping, U-turns, and a lot more to come. You'll see it. And now you'll see the reconstructions of some of the flights.
So now I'm going to run this multi-camera self-calibration algorithm by Soboda. It's modified by our PhD student Yihao. So we will get the LED path in the tunnel in order to get a 3D reconstruction of the bat. So here's the result we will get eventually.
Behind me, this is the array tunnel. It's composed of 50 cameras and 35 high-frequency mics. Using this instrument, we are able to collect large amounts of data through bat flights and also be able to visualize them and hear them at the same time. This is the data that we can see are active chirps from a hippercitrus bat. You can see a clear chirp of 120 kilohertz and is viewed in a spectrogram. Allowing us to capture and record this data through our National Instrument DAC system allows us to hear the bats at maneuvers in case we put obstacles in front of them. An additional purpose of capturing this data is to also localize the bat in the tunnel. And we do that by calibrating the tunnel through a rasterization test using our BatBot right here. This BatBot, we put it as a XYZ grid, and we pinpoint down the tunnel to calibrate the tunnel. And using a model, we can input a XYZ position, and from that, we can collect the visuals of the bat and also the acoustics as well. So we can actually hear how the bat is moving and how it's sounding like at that maneuver.
And I will be explaining the Sonar bot that we'll be using for this project. The most important parts are the transducer and the speaker. The transducer mimics the bat's ability to emit ultrasonic sounds. So this is what our BatBot is sending out, which will be the chirp, which is a sweep from 1,000 all the way down to 30,000 kilohertz. And then we have our reflection, which returns. In this case, it was from a wood pallet set up at 1 meter away. And we have our return of our reflection almost perfectly identical at 1 meter away. Another feature that we have is the ability to run a live spectrogram. And then we can see that there is an object that is reflecting the chirp back at it. And this I will show now, raise the pallet around 1 meter. And then I will move the pallet back, and we'll see that it also moves back and it also moves forward.
We developed a method for pairing GPS and sonar data in collaboration with researchers at Virginia Tech. We took our BatBot into the forests of Brunei to simultaneously gather sonar and GPS data. As the sonar chirps reflected off of the surrounding foliage, they created unique spectrograms, and using this data with machine learning, we're able to pair the spectrogram data with GPS to pinpoint exactly where we are in the forest.
This is made possible through the use of RTK, which is a method to collect super accurate GPS data down to the centimeter range. This is done by using a base station and a rover, the robot. The base station collects correction data and then transmits that data to the rover over a local area network. The rover then uses this data to be able to accurately locate itself. This should allow us to get close to our ultimate goal of creating an alternative to GPS, which can be used in places where satellite access is thin or in just generally hard to reach areas.
Here I'm working with bat robots, and specifically our flight bots that we're working with here. Currently we're working on replicating flight of a bat in robotics because bats show great agility when flying through the air. The current bot that we're working on is about great, and it's a fully flight sustained bot. Now that we made it, we are now currently working on evaluating the bot, which includes doing a kinematic analysis on the bot, which we will then compare to an actual bat to see what's the next step in improving this design.
We use the video data that we get from the flying bat and the BatBot. We use that data to process it through DLC. DLC, or Deep Lab Cut, is an open source toolbox that helps us with tracking the movements with very high precision. So after using DLC, we can then use the Hurst exponent and potentially AlphaZero to see how we can make sense of the data. And by calculating the different points on the bat and the bot, we can try to understand how the wings, how the BatBot and the actual bat differ and are similar.
We're the biologists of the team, and this is a harp trap. We usually set this up before sunset so we can catch our bats of interest that we bring into the lab for our experiments. Our bats of interest usually come out of their roost right before sunset, and they're usually Hippocyterus and Rhinolophus bats.
So the way this works is we'll set this up in the forest, and this will have 4 banks of these strings called harps. The bats fly into the harps like this, slide down the strings, and get collected in a pouch below the trap. We'll pull them out for processing. This has been a pretty typical way to catch bats since the 60s, and it was invented sometime in the States. So we've traveled all across Brunei to forests in the 4 districts to catch our bats. We've gotten over 40 over the course of the summer, the majority of which have been the bats of interest.
Hey, hi, I'm intern 1. Being here has really made me think about my future as well, and I think it's been a really fun experience.
Hi, I'm intern 2. During this internship, I mostly did the data collection stuff. So in that process, I also learned a lot about Python coding, and that really helped me explore an area that I have never explored before.
Hello, I'm intern 3. I got to dabble in a little bit of everything. So I got to learn some coding, MATLAB, DLC, and I think there is stuff that could help me a lot in the future, especially since I'm going into the engineering stream.
And cut.
That's okay, right?